Okay. All right. I'm going to do it differently, so I just make sure it does work this way. All right. Very good. Go to continue. All right.
Okay, so let me start off by making an announcement. So hello everyone, thank you very much for joining us today. So as let me start off with some administrative stuff. As you all read in the email, if you ordered food for tonight, because we can't get pizza, we will be reimbursing you up to $8 for whatever you ordered. And so in order to get reimbursed, though, you have to provide us with your name, your email, and an address that we can ship the check through. And the reason why we have to ship a check is because this goes through the school. And so in order to get that information, I just posted a Google form. Here, I just posted a Google form in the chat. So now, like if you feel comfortable, please fill out the Google form so we can reimburse you. I know there's some concerns about filling out a Google form. So if you'd rather not have that information in a Google form, feel free to email me all the information to my email that I just put in the chat. Are there any questions regarding that? Awesome. So let's begin. We're very lucky to have Professor Chin with us today. Professor Chin is a professor at the University of Chicago. He earned his BS in physics from National Taiwan University in 1993, and then earned his PhD from Stanford in 2001. He spent 2 more years at Stanford doing postdoctoral research, and in addition to joining U Chicago in 2005, he has been a visiting professor at Rice University, MIT, and the Max Planck Institute, to name a few places, among many others. His work focuses on experimental atomic, molecular, and optical physics, and he has studied Bose-Einstein condensation, strongly interacting Fermi gas, thermophoretic levitation, and novel quantum states and quantum dynamics, to name a few research areas as well. Today, Professor Chin will be discussing how to discuss a quantum time machine. And now, for a brief moment, please unmute your microphones to give a warm welcome to Professor Chin. Thank you.
All right. Thank you. Thank you for the opportunity to talk to you about some of the ideas we've been thinking about. And I'm an experimentalist. So I actually want to think about something that is practical. It is sometime in the near future. So I kind of pose these questions in the abstract. So I guess hopefully you have seen that. So this is on a very tricky issue. Okay, so many of you might think, okay, well, I could be talking about science fiction, but I think this is at some point, this is a point that we can really think about this seriously. But I would first like to point out a lot of things that you learn in classroom. Okay, when you start to learn in this more and more this stuff on classical mechanics, E&M, quantum, and so on. Okay, some point try to bring them together, and they are cracks. There are some kind of inconsistencies at the interface between these subjects. Okay, so and this is one of them. And I would like to start from the very beginning, based on this what you have learned in this classical mechanics and so on. All right, I'm going to do it in a different way. I'm going to switch to my. I need to figure out how to go back in. Okay, go back in time, I guess. How do I go to previous slide? Let me think about how to do this. Okay, this is not good. Okay, I'm not supposed to show. All right, now I see it. Okay, all right. So I think we're all fascinated by that idea. Okay, this time traveling, and you also know that lead to paradox. Okay, and we learn physics. We know how the things are evolved. We are making predictions. Okay, and we like to see how well we can control system from macroscopic world down to microscopic world. So based on what we understand, is it really possible to reverse the evolution? All right, and you'll be surprised even from different theory, have a kind of a different that you learn. Supposedly in this on the textbook, they should be. Okay, now I should move to the next slide. There should be consistent kind of result, but turns out it's not. All right, but before I begin, I would like to say here, I'm not going to talk about something that is kind of a topological structure of this space-time or this kind of novel theory in cosmology, wormhole. I'm not going to talk about any of those, or those are the physics that we do not understand yet. Okay, or the physics I do not understand. Okay, say quantum gravity string theory or new age theories. Okay, all right. I'm going to just focus on what we can what we learn from standard textbook. All right. In particular, say start from classical, move on to thermal and to quantum. Right. And second, I want to define what I mean by time reversal. Okay, I think this is a kind of fancy concept you might have, but there's a lot of arguments based on the bad definition, what we have in mind, what time reversal would be. I'm not talking about you can reverse the arrow of time. Okay, so time is moving forward. Somehow you can do something, the t become minus t. Okay, I'm trying to provide a definition in the following way. Okay, what I mean by time reversal. Let's consider this kind of space-time diagram. Okay, and let me see, where's my laser pointer? Yes, this is it. Okay. All right. For example, at some point, just some particle, say in this case 3. Okay. All right. As the time evolves, okay, then they might interact and so on. Okay. And then when I say time reversal, that means what I mean is at some point, say t equal to 0, I want to do something to the system. Well, I might give myself full freedom, say give me some time, say within epsilon amount of time. I do something to the system, such that afterwards, this particle is going to evolve backwards, such that for t, for time larger than epsilon, okay, larger than 0, on the right-hand side, the evolution will be the same as the evolution as if the system going backward in time. All right. So the question is there something we can do at t equal to 0, such that the evolution for t larger than 0 will be the same as evolution going backwards, moving backwards. T time is still moving forward, okay, but just a particle moving back, particle moving forward in time, as if the particles are moving backward in time. So this is what I mean by this reversing the evolution, okay, or reversing the time. Okay. All right. So let's first look at this diagram. It's already clear if we just treat these as classical particles, okay? And at some point, say we can imagine just reverse the velocity, right? If we reverse the velocity, then the forward moving particle now moving backwards, okay? Then you say they interact at this point, okay? Now they are separated. If you reverse the velocity, at some point they are going to collide, okay? At the time that exactly the same as on the at an earlier time, in principle. Okay. Right. That'll give you the first hint just from intuition. In principle, all you have to do is very simple. Okay. It is from a classical point of view. Okay. Let's see whether we can formulate this based on what we learned in this classical mechanics. All right. So what we learned in classical mechanics that the equation of a particle satisfy this this Newtonian dynamics, the Newtonian equation. It's a second order equation, F equal to ma. A is the second time derivative of respect to time. And then the force, where's the force coming from? Typically the force coming from some kind of potential, right? And then you will drive the particle toward the lower potential. Okay, so you do the derivative with a minus sign. And I put in xi. In principle, this formula applies to n particles, and there are 3 n coordinate x, y, z. Okay, for convenience, I just label them as I on 1 to 3n. Okay, you can stop me anytime if you think there's any question here. Right, so this is a equation, it's a differential equation. And we know, I think you'll learn about this. Once you know the initial position, initial velocity of all the particles, and then the differential equation is given. Okay. We need to know both the position and velocity because the second order equation. Right, and then let's suppose this at t equal to 0. Okay. Then for t larger than 0, then there's a unique solution. It can be complicated, maybe hundreds or thousands of large number of particles. So in principle, okay, this the boundary condition t equal to 0, and the equation itself will tell us how the system will evolve in later times. Now let's try to apply our this intuition. Now, if we somehow flip the initial velocity from you don't need to change the position. At t equal to 0, okay, we change the velocity. Do we need to change anything in our equation? We don't, because t appears twice. Okay, this is dt squared. All right, so you can show with this with simple math that all we have to do is change the initial velocity. Okay, you free the sign of the velocity, then the particle will also evolve according to the Newtonian equation. And then at a later time, t larger than 0, the behavior will be the same. Say 1 minute later, then you see the particle. The particle will appear to be 1 minute earlier. Any questions so far? All right, good. Okay, this is how you can understand this problem mathematically. This is quantum mechanics. These are classical mechanics. All right. Now, before we move on to talk about this, what really defines the time, that kind of unique define the time, thermodynamics, let me move on to quantum mechanics. It's not much more complicated because quantum mechanics is also described by a differential equation. But now we're talking about Schrödinger's equation. Here's a wave function that defines the state of the system. The system might have 1 particle or fundamental particles, or it can be many, many particles, say a quantum many-body system that in quantum information, people want to handle these many particles or complicated material and so on. So wave function, in principle, we believe Schrödinger's equation also apply to many particles. And what's this? This Hamiltonian that determines the evolution of the system. And that contains the kinetic energy, the p squared over 2m. Okay, of course in operator form, but for this for here, it's sufficient to think about the kinetic energy term. There's some kind of potential energy, the same as before, interaction energy. So you tell more particles, they can also interact. Again, this is a differential equation. So, but this is a first order differential equation. We don't even need the velocity. All we need is that the initial wave function. If the initial wave function is given, and then we are also given the differential equation. In principle, you can predict, or the wave function at a later time, okay, it determined. Okay, it determined. All right. How about you want to reverse? So you want to reverse the evolution. Want to say 1 minute later, then wave function will be the same as 1 minute earlier. Okay, we are given a boundary condition t equal to 0. Now looking at this equation, actually we don't need to do anything to the wave function. Okay, but now this is a first order equation. If you consider t become minus t, is equivalent to change Hamiltonian to minus h. Yeah, okay, minus h. Okay, so now you can see that given a boundary condition, that's a t equal to 0, and then if you can free the sign of Hamiltonian, okay, Hamiltonian include all these 3 terms, and change the sign of the kinetic energy, change the sign of the potential energy, change the sign of the interaction energy. If you can do this, in principle, okay, evolution, the system evolve backwards. Well, system is still evolving forward in time, but 1 minute later, it looks like the system is 1 minute earlier. before 0. All right. Before I move on, any questions so far? All right. Good. So let me move to the next slide. All right. So I think you are probably not surprised to hear that classical mechanics and quantum mechanics all essentially respect time reversal symmetry. You need to do something, okay, and then you can reverse, and that way we all know these two theories, okay, does not really distinguish the direction of time. However, before we really talk about how they contradict with thermodynamics, you might already notice the condition to reverse a time, okay, is actually different for classical mechanics, quantum mechanics, right? In one of them, you only need to change the velocity. In the other one, somehow you need to change Hamiltonian, which is much harder. In the first case, you change the velocity, you don't need to change the environment, you don't need to change the potential or anything. You don't need to change kinetic energy. In the second case, your quantum mechanics is correct. You need to change the sign of kinetic energy. That means to say you change the mass to be negative mass. You change the potential. Yes, in the beginning is a positive potential. You want to make go to negative potential. You also need to change this interaction. If there's a attractive interaction, you need to change out the repulsive interaction. So how is it possible that this two theory, very well-known theory, somehow is a very different recipe? Okay. Or can you think of example? This say now this now you see in this photo, this glass is broken into small pieces. I think this is by vibrating a very high frequency, essentially hit the resonance and then break into pieces. So now, in principle, I think in reality, nobody can reverse a kind of broken, breaking glass like this. But let's set apart all the technical difficulties. One day our technology will be good enough. One day we can record all the velocities. We can record each small piece, where they are going. Now let's ask the fundamental questions. Is it sufficient if I just reverse the velocity of all the fragments? Will this glass come back to normal, or do I need to change the use of quantum mechanics recipe, change the mass, change the interaction, change the potential? That seems to be much harder. All right. So already it's strange. You say, well, this glass is a classical object. Probably we don't need that, right? Okay, why do we need quantum mechanics if you only talk about classical piece of object? But fundamentally, you see, well, the glass is made of this silicon oxide molecule. The way they are bounded, the molecules are bounded based on some kind of molecular interaction. Probably we do need to consider quantum mechanics in the microscopic level. All right. So any of you want to have a kind of a simple any kind of simple idea to reject, okay, the classical mechanics or to reject quantum mechanics? Okay, whether that recipe, let's say this for classical mechanics, is there any example you can show that if you only reverse the velocity, then it actually cannot bring the system back to the initial state? I would like to stop here for a few minutes. Okay, any?
So you want an example of where just reversing the velocity classically won't time reverse? If there's like some sort of friction that depends on like v squared or v, like if you just reverse the velocities, maybe you're going to be losing energy both ways, and it won't respect the time reversal symmetry.
If you go from v to minus v, in principle, energy will not change, right?
I was thinking like maybe like a fire or something, something with some sort of, or like enzymes and enzyme reaction, like something with some sort of activation energy, that you have to achieve. I guess like in theory, if you reverse all of the velocities, the kinetic energy should achieve that activation energy. So maybe that doesn't work. I don't know. I'm not quite sure. I just thought like, or maybe like a system where like the entropy of that system increases in some way. But I'm not sure.
But in principle, if you only change the velocity, energy shouldn't change. Entropy,
Yeah.
all those thermodynamic quantity also should not change.
Okay.
Okay. I'm going to give you a simple, give you one example. Perhaps you can see that very quickly. That classical method actually does have its limit. Okay. Let's consider this a laser beam. Okay, and they send that to a beam splitter. There's some partial transmission and some reflection. All right, let's put put a mirror. Ideally, this mirror will reflect the direction of the light. Okay, now these two light beams will kind of will meet each other. I assume this distance is exactly the same. All right. So now here's the question: whether the beam will go back to the initial path, or will go into this, or go into the false path, the empty path. So this is the example that you actually learn from this classical mechanics or kind of waves, kind of wave dynamics. Okay. This in the barometer. Okay. So it shows that actually reversing the momentum is not quite enough. There's something also called a phase. However, classical particles do not have such kind of phase, and say, well, this photon do not belong to this classical mechanics. But if you really think about, even in the case of fundamental particles, you can also build in the barometer because they are also matter waves. So in reality, reversing momentum is quite enough. This case shows that it also depends on whether there is the relative phase is correctly built up. Okay, to see the constructed interference, the destructive interference. Okay, so I'm going to stop here. You can also think more about this. For this example, you kind of have classical. To understand matter wave, you do need to borrow the idea from quantum mechanics. Okay. All right. Let me move on. Okay. Go to this, the broadcast. And where is my slide? All right, good. So I think in both cases, you can see that there is nothing defines the time error. Okay. In both cases, if we can do reverse velocity for classical system, or it can really change the Hamiltonian or quantum mechanical system. Okay. Both theory will allow time to reverse, will allow the evolution backward in time. The only thing actually at the moment, the only thing that we know that really define the time error, okay, at least two of them, but depending on who you talk to, these two are probably the most prominent ones. One is thermodynamics. You can think about this a very simple example on the right hand side. This if you remove the barrier that separate a gas from vacuum, okay, then this diffusion process will always diffuse into a lower density portion of the chamber. Or you can think about these are not really particles; these are some energy quantums. Okay, so energy quanta. So the heat diffusion, you always see energy flow from hot to cold. So this is called this is second law of thermodynamics. In a more formal way, if you can see how in different textbooks, they have this how people phrase it in different ways. It's certainly this a more modern textbook. This is the statement. If you consider an isolated system, entropy can only increase or remain the same. Entropy will kind of characterize the randomness of the system. To some extent, that the left-hand side is more organized, okay, because there's nothing on the right-hand side. They all come to the left. Okay, the right-hand side is less organized. In principle, each particle have a 50% of the chance to be found on the left side. But once many particles, then it's unlikely all the particles are found on the left-hand side. Okay. Already thermodynamics developed to handle many particles. That's a very important hint. Okay. Even though fundamentally this each particle obey, say, this for thermal system, high temperature system, obey this Newtonian dynamic. At least that we know it should be effective. Even though it's a quantum particle, okay, fine. In principle, they follow the Hamiltonian Schrödinger equation. However, this is it consider a law. That means I don't even need to do any derivation. You either you need to accept it. Okay, if you studied thermodynamics, that is a law. Okay. The second way how this time error defined, a lot of this more modern way, because the universe has been expanding since the beginning, since the Big Bang. So you say, well, if you just look at whether the universe is expanding or shrinking, then you can tell whether time is evolving forward or backward. But I had to say, I personally do not really like this this definition of time. Okay, it's just say if I'm living in this world, okay, when the system is when the universe is expanding, just I see the sun always rise from the east. I say, well, all you need to see which direction the sun rises, then you can determine whether you are moving forward or backward in time. So I'm going to stop talking about cosmology. Also, I'm not a cosmologist, but let's try to more focus on the time error defined by thermodynamics. Why fundamentally this is reversible, but practically you never really see a complex system evolving backward in time, or anything we can do if we can truly do so. All right, so let's see where is this coming from. Well, if I'm in the class, okay, then probably don't ask this question. Then just do it, and just take it, and when you just write your homeworks. Well, but if you're a true believer of classical mechanics, you say, well, maybe the second law of thermodynamics comes up just because the practical reason we cannot precisely reverse the velocity of all particles. It's definitely impossible if you want to reverse the velocity of all molecules in the room. Okay. But even in the more just in a simple system, okay, when you can remeasure everything, all the particles, say 10 particles and so on, okay, we'll say there is something that's supporting this idea. Okay, you cannot, you can practically is always sensitive to small kind of deviation, okay, small imprecision when you want to reverse the velocity. Okay. So any kind of imperfection that would if we do believe that we can control the Hamiltonian, let's start with the regular Hamiltonian. A lot of systems evolve over time, tau, from the wave function the minus tau to wave function equal to 0. And if we also believe in thermodynamics, then we know entropy will increase, will remain constant or increase. But if you consider kind of crazy system, like the one I show you, the breaking glasses or releasing the particle into free space, the entropy definitely increasing. Okay. All right. Now, assuming we really had a capability to change Hamiltonian minus h. All right. And then, well, the system evolved backwards. If that is the case, then this capability would suggest we will violate the second law of thermodynamics because entropy is not decreasing. Okay, but then you can also ask if this whole process is described by quantum mechanics. Then can we also why can we also evaluate entropy based on quantum mechanics? What will happen if we evaluate the entropy based on quantum mechanics? Then it turns out what you're going to see is that the entropy is going to be constant throughout the whole time. Even for those crazy situations like explosion and the diffusion particle into an empty space. Okay. So the concept of entropy is questionable, depends on how you look at it, whether you look at it based on thermodynamics or based on quantum mechanics. But nonetheless, if the system really works, okay, from a classical kind of point of view, if you can reverse the entropy, well, that would be surprising. Can anybody do that? The answer is still no. Okay, not at all. But that's nothing. This is what we want to do. If you really reverse everything, say this. Let's try to go to the next slide. Okay. So here's one sentence, one saying from Richard Feynman, talking about the difference between the thermodynamic entropy being increasing, but quantum mechanically the entropy remains the same. Okay. All right. So he said, you know, the most amazing thing happened to me tonight. I saw a car with a license plate ARW357. Can you imagine? All the millions of license plate in the state. What was the chance that I could see that particular one tonight? Amazing. Okay. Do you see the connection? You can imagine you are the one sitting at the corner. Okay. And then if you had no prior knowledge, you know nothing about anything, you think this the next ball coming to you is random. You see there's a large entropy. However, you can also say that particular license plate or particular car you see or particular ball you see, okay, is well defined by the theory. Is the theory deterministic? The entropy is also zero. Okay, I'll let you think about this. Okay. All right. Now let me move on to the second part. How do we really build a quantum time machine? And by quantum time machine, we say we want to have a system that can really evolving backward in time, and will follow the more strict condition based on this quantum mechanics. But this can be done on many body system, and then we are going to show that there will be the violation of second law of thermodynamics. All right. So as we just mentioned, in principle the recipe is simple. Okay. Say you start with a system, you know the past, but you are given the system at t equal to 0. Okay. Once you know the past, you also know how the system evolving. All you have to do is just freeze the sign of Hamiltonian. How we do that as experiments, I will mention later. But in principle, if this we can do, then we're done. Okay. Then a later time, this wave function will be the same as the wave function, kind of at t equal to minus tau. All right. But it is the same as what we call time machine. It's actually not. Just think about this. That consider if you can really reverse the evolution of the whole system. All right. So the system go back in time. Your memory also go back in time. Everything go back in time. So now I try to do this experiment, try to reverse time to yesterday. But when I go back to yesterday, I totally forgot about, because my memory is also being erased. There's no trace left. So this is actually not what we want to do. We don't want to evolve everything backward in time. If we evolve everything backward in time, you also wouldn't notice, because you are going to lose all the memory. Okay. So time machine is more tricky. Time machine is something like you want to have this reverse of time only for your sample, or one day only for your customer. Okay. So you don't want to reverse everything. You only want to reverse a subset of the system that you care. Okay. All right. And that sample that talk about, we use the wave function for the sample. Okay. That sample is going to evolve. Okay, to time t equal to 0. And then we want the sample to follow the evolution, okay, going backward in time. So you see the Hamiltonian, now there is but the lab, so say the experimentalist should evolve forward in time. So Hamiltonian for the lab will be HL. We don't want to change the sign for the labs. So you want the rest of the world to evolve forward in time, but the customer evolve backward in time, or the sample evolve backward in time. So you can verify there's a time machine, right? You don't want to evolve everything backwards. Of course, we cannot evolve everything backwards. We cannot even do this on a small sample. But in principle, this is what you need. Okay. All right. So only reverse the sign for the same Hamiltonian for the sample. Remember Hamiltonian for now. Just think about including kinetic energy, potential energy, interaction energy. Okay. So only within limited space, you want to change the sign of the Hamiltonian. All right. So if this doesn't sound bad enough, now let's think about the following. The way we control the sample is that we need to do something to the sample. In order to do something to the sample, you need to have an interaction between lab and the sample. Okay? So we are using this term where we need to turn on our time machine. We need to do something to the time machine in order to reverse the evolution of this HS. So now this interaction between the experimentalist and the sample, now I call it HLS. Do we want her to flip time? Do we want her to flip sign? It's actually unclear. But this term include the interaction between the sample and the scientist. Okay, so that means this term include the interaction, include the kind of how the two systems are talking to each other. We need to do something to the system, for example, to change Hamiltonian. Okay, all right. So the additional difficulty, this is what we do to the system. Do we need to? How are we going to handle this term? Because one of them need to flip sign, the other one need to, one of them cannot flip sign, the other one need to flip sign. So what are we going to do with this interaction term? Okay, I'll also leave that to you to think about it, or maybe you have a better kind of protocol how to really do this. Okay, yeah, but let's first focus on the earlier question. Is it really possible to reverse Hamiltonian? Hamiltonian for a simple quantum mechanical system, that forget about kind of field theory, forget about this ENM kind of just talk about simple, say kind of this simple system where the Hamiltonian only contains 3 simple terms. First one, p squared over 2m, and the flipping momentum is not good enough, right? You cannot change 2 to -2. How do you change 2? So only thing you can change is you need to change mass. All right, so you make all the mass to be negative, then you change the first term. How is that possible? Second, you need to change the external potential. Okay. All right, perhaps there's something we can do to change the external potential. You can use the electromagnetic field to define some kind of potential. In any case, electromagnetic field is the source of a lot of potential anyway. Lastly, you need to change the interaction. How are you going to change the interaction? Say if this gravitational interaction, how are you going to change the sign of gravitational interaction? E and M, that's possible. You need to change the charge. But how are you going to change the sign of the charge? Okay, so it looks like this is impossible, right? But if this is impossible, then I wouldn't be here. So I want to tell you, now it is possible to change all 3 terms. Okay, it is possible to change 3 terms. I will show that in a couple of slides. Lastly, you want to do this in a non-trivial system. If you only study, say, the interaction 2 particles, collisions, or 2-3 body collisions, then people will not be surprised. Okay, we know fundamentally this few particles, they can be reversed. So you want to show this, or want to compare to thermodynamics, you need to prepare a system that contains many particles, and there are interactions. If only many particles, they are all independent particles, that ideal gas and so on, then you can imagine that is also simpler. Lastly, also many degrees of freedom. Okay, many particles, okay, interaction might not be enough. You also want to have many degrees of freedom. For example, you have a laser beam, there are many photons, but they're all in the same mode. Okay, that will also be boring. Okay. All right. So lastly, the last difficult part, you want to identify the system that you can really control these three terms on a many particle system with the interaction and multiple degrees of freedom. Okay, so now let me briefly mention outline what we are going to do. Okay, and want our system to be like a breaking glass. Okay, all right, which you think is impossible to reverse. Okay, so the story came back to the kind of the student of mine who graduated 2 years ago. Yeah. What he demonstrated this when he was in Logan was in my group, he showed that there is actually he identified a new way to control atomic interaction. Okay, it's called phase bar resonance. What he demonstrated, you can use a laser to control the interaction between atoms, make it repulsive or attractive. Okay, so that's the last term. Okay, that's last term. We can change the sign of interaction with some tunability by controlling the laser power. Or later, we also show that this, we show that we can make the interaction be positive, repulsive, or attractive. A neutral particle is possible. Okay, the neutral particles, say these atoms and so on. For electrons, it is so very difficult. I don't think people can kind of change the sign between two electrons. Second, how we're going to change the kinetic energy. That you might think is the most difficult, how we can make the mass to be negative. Fortunately, there's a solution from condensed matter. I think when you learn condensed matter, this we learn about band structure. Okay, so condensed matter, say if you have a loaded system, the system say in the lattice configuration, energy would depend on momentum in different ways. Typically, you see the curvature positive. This is equivalent to p squared over 2m. Just think about the horizontal axis as momentum. So the positive curvature. Okay, that means the mass is positive. All right. So our solution to reverse the second term is to drive a transition to a higher band. So this band structure has a kind of different situation that some band might have a negative curvature. Equivalently, you prepare the system here with a negative mass. Okay, and this is something we and I write down the kind of quantum mechanical way how the driving can work and convert particle into a different branch with negative mass. That's the second term. And this we can experimentally we demonstrate that we can go from a positive curvature to zero curvature to negative curvature. But then you say what happened to the side? So for now we're only going to focus on this small momentum. For small momentum, we don't care about this other kind of crazy structure. Okay, so we're going to prepare very, very cold atom with very, very low momentum. So we only care about the momentum, okay, near k equal to 0. Okay, so that's a way for us to change the second term. Sorry, to change the first term, the kinetic energy term. All right. So combining these two, what do we this capability? What do we have? Okay. So this is also Logan's work before he left our group in 1 year before he graduated. He loaded this atom into a very, getting very, very cold. So only care about very low momentum, and confined into a kind of a cylinder potential. Okay. Inside the cylinder, essential potential energy is 0. So it can change the sign. Okay, but you can say, well, then how about the wall? Okay, but the wall is very, very high, so we can ignore the particle that very, very close to the wall. Okay, so it's mostly looking at a sample within the inside the box. And then now that's the last question. Remember, there are 4 questions. The last one, we want to make a system interesting. It's similar to kind of breaking glasses. So what he realized is that we can use this phase bar resonance to control the atomic interaction. We actually we try to make it oscillating. This is a crazy idea coming from him. Made the interaction repulsive for half the cycle, attractive for the other half of the cycle. Okay. And why do we do that? Actually, he was just having fun playing around in the lab. All right. And these are initial
atom, initial kind of distribution atom inside the box, the circular box. Okay, about 10 to 5 atoms, and then radius about 10 micron and so. Now t equal to 0, we start to do this modulation. What do you see? Come on. All right, I'm going to show you this movie. I'm hoping I can show the movie. Oh my God. All right. I think somehow movie disappearing here, but I'm going to show you the result. No, it's a movie showing. So we see that when we do this modulation, after a few tens of milliseconds, suddenly a fraction, typically 30 to 50% of the particle kind of break loose and emit in all directions. Okay, this we call both fireworks. Okay, and then this is one snapshot. In the beginning, everything in the ground state, zero momentum. After some time, they form this very narrow jet coming out of the condensate. Okay, and we studied this jet for some time. Look at all kind of distribution and so on. But fundamentally, this is similar to breaking the glasses. You can think about the glass in the beginning, all the molecules in the ground state in some form. And suddenly, you try the system with this modulation. You suddenly you reach a threshold, and then the glass kind of broken into pieces. In our case, about 50% of particles just break loose and go in all directions. Every time you perform the experiment, you see a different pattern. Okay, and it is because every time you see a different pattern, you can soon define the entropy, right? Entropy is the randomness. When everything is well defined, like this, okay, then you can say the entropy is very low. At the later time, okay, when the system break loose and kind of form all these structures, there's a lot of entropy. But at the same time, this is also a quantum mechanical process. In principle, entropy should not increase. All right. So let me quickly jump to our now question is whether we can reverse. Okay, classically say this from thermodynamics, that this is impossible. From classical mechanics, you need to reverse the velocity. We also don't have that capability to reverse the velocity of all atoms. However, we can control the Hamiltonian. I write down this quantum model. This may be a bit kind of you might need to go to advanced quantum mechanics to understand the symbols here, creation and negation operator and so on. But let me just put this into these simple terms. The first one describes the atoms. Atom is the one we want to reverse. Second one describes the photons. When you do the modulation, we introduce photons to interact with the atoms. That is the lab. That is the one we don't want to reverse. Remember, you want to reverse only the Hamiltonian for the sample. And last one, this is the atom-photon interaction. That is one that's tricky. We don't know whether we should reverse or whether we should not reverse. We try, okay? And now the question is whether the Hamiltonian describing the system like this, okay, allow us to reverse this firework emission. Quickly show you the result. First of all, we show that if you do the analysis, try to see how the emission fraction and so on, okay, we can quickly show that the moment we see the emission, there is a fast increase of the temperature, okay, from almost 0 microkelvin to about 2-3 microkelvin, okay. So this process accompanied with a strong heating. Just like when you break the glasses into small pieces, there's a lot of energy transfer to the system. Indeed, the system seems to be heated. We can also show that entropy is also increasing, okay, by some 200 kb. If they evaluate entropy based on classical method, okay, from thermodynamic entropy, then it is increasing. All right. Now what can we do? Now we want to reverse the Hamiltonian. Okay, if we can perfectly reverse the Hamiltonian, then what do we see? We are supposed to see that when we go forward in time to here, and at some point reverse Hamiltonian, then system will come back. Okay, and if I can really reverse the evolution of many body system, I also wouldn't be here. Okay, but I can show you how far we can get. So for the first about kind of a 4 or 5 milliseconds. Now this is what we do. Okay. And that we do the, so you can see in the first 4 or 5 milliseconds, we start to see the emission, this total particle number being emitted out of the condensate. Okay. If we continue this evolution, then you see the system there are more and more particles being created. The system will also be heated more and more. However, at 4.8 milliseconds, we try the reversal. What we do is that we suddenly change the way we perform the modulation. So think about this a little bit like a swing. You try to push it in the proper way. Then you see the amplitude of the swing is getting larger and larger. At t equal to 0, you suddenly change the phase, how you modulate, how you push the swing. Okay. All right. In principle, this if you do it perfectly, then what we should see is the reversal. And what can we see? Okay, we tried this experiment for about 4 months. We can see a tiny bit reversal. You can see the red curve. Okay, and if you don't really believe in just a data point, I'll show you the image. If you do not perform this phase jump, if you continue the blue curve, now you can see the emission getting stronger and stronger. You move to the right, getting stronger and stronger. But if you perform this phase jump, okay, suddenly you change the way you perform the modulation. Okay, now you see getting stronger and getting weaker just by about 10%, 15%. Okay, and afterwards it becomes stronger again. So we see a very weak reversal. Okay. Nonetheless, this is so far we are the best we can do. We can show the entropy is continue going up, but the moment 4.8 milliseconds when you change the phase, we see within our error bar maybe about 2-3 sigma, we can start to see it looks like entropy goes back a little bit by less than 10%. So going from 4.75 to 4.5. It's a tiny effect. Okay. However, we are very excited about this. Now, for the first time, you show even 10 to 5 particles, they are interacting and so on. Now, we can see a small reversal entropy by 10%. Okay, and the temperature, okay, is reduced by about 20-30%. So this reversal correspond to moving backward in time for about half a millisecond. Okay, in terms of entropy. Okay, going down to this level. If you ignore the error bar, roughly to about here. Okay. All right. Let me see, do I have any more? Okay, so I'm like to kind of conclude. Okay, so first, how do we describe what's going on here? If you think about this experiment in terms of thermodynamics, we are essentially emitting some kind of trying to shake the atoms. We do the modulation on the atoms, and this external modulation heats and also increase entropy in a way that what you do to a kind of this any cold sample if you perform kind of transfer energy to the system. And then from that, we can see how temperature increases. It follows us this thermodynamic distribution very well. Okay. However, we were able to reverse the entropy, okay, by a tiny bit. Okay. By the way, this entropy evaluated based on this thermodynamic method. Okay. By just changing the modulation, so essentially similar to kind of pushing the swing, but suddenly change the phase. Quantum mechanically, okay, the description is very different. Quantum mechanically, you start with say assuming particle in the ground state, and now you evolve forward in time given Hamiltonian. Now we are really reversing every single term to the Hamiltonian as much as we can, but we don't have a perfect way to control kind of the Hamiltonian yet. Okay, and we're not sure whether we're limited by the experiment or by some other more fundamental reasons. But this firewall, in principle, it doesn't really the quantum mechanical descriptions that there's no heating. The heating is a result of this some kind of quantum entanglement. This particle that created all these kind of structure and so on is just a complicated quantum mechanical state. Okay. That non-locality, now kind of a entangled pair being created. But if you can do it properly, then you can reverse the evolution. Okay, the system never really go to high entropy state. You remain in the same initial state as the low entropy state. All we do is just evolving the system according to a new Hamiltonian, and that new Hamiltonian has a kind of effect. This is also called many body echo, bring the system back to the initial state. All right, okay. So that's our current understanding, and this is our system. And I think just come back to this last slide, okay, and see whether any question I would like to about the slide. All right, thank you. All right.
So yeah, I actually have 2 questions. My first.
I somehow couldn't hear you. I need to figure out a way how to do this. Let me log out and log back in again. Just a moment.
That's good. Oh, by the way, if anyone has any questions, feel free to raise your hand, and I'll call.
Can you try to say something?
Hello?
Hello?
Can you hear me?
How about you can type the questions in the chat? Okay, thank you. All right, so there's a very good observation. We see the entropy decreases, not by much, and then it increases again. Okay, our understanding is that this, in any case, this modulation. Think about the swing as an example. Okay, you push it, okay, and but how if you suddenly change the phase, okay, and then you somehow can reduce the amplitude. But if you continue pushing it with a new phase, then the amplitude of the swing will go up again. Does that help?
If anyone has any questions, feel free to raise your hand.
You can try to speak again. Maybe I think I got my. Yeah, I think I can hear you now.
Can you hear me?
Yes, now I can hear you. Good.
Okay. Awesome. Yeah. Does anyone else have any other questions?
So is the reason that we're not violating entropy increase because sort of by nature of the process, you're like connected to like an external reservoir. So it's like entropy shouldn't always increase.
Okay. No, actually not. If the system connected to the reservoir, okay, then whether entropy increase or decrease will depend on the reservoir, right? It's just like if we put food in the fridge, entropy can decrease. Right? So for more careful discussion, we always need to consider isolated system. Yeah.
I guess I have another question. So in that moment when, or in that time, that brief time period where the entropy decreases, how do we know what's occurring is a brief time reversal of the particles as opposed to some other process causing the entropy to decrease?
Yes, in principle, it is possible to evolve in a different way. Okay, so if we can do the experiment like perfectly, okay, say we can reverse entropy all the way back to 0, okay, because ground state is unique. Okay, so you can go back to the same initial state, but it might not follow exactly the same path. Okay, so far we have not been able to kind of verify whether it is following the same path going back. So what we could do, so how do we measure entropy here? What we do is that we analyze this emission and we can plot out their distribution. Okay, plot their distribution, then entropy defined as probability multiplied by log probability and sum over all particles. So we are using this classical this formula to evaluate entropy.
Got it.
I have a question about the Hamiltonian for like the Bose fireworks.
Sure.
For the interaction terms, like the like B dagger, like the coupling with the environment.
Yeah.
So you left the sign of that unchanged, correct?
We actually do change that, but in the way that is probably not very obvious. Okay, let me see. How do I go back to there? Okay. So let me see. So here's a tricky part. So look at this. It looks like we always perform the modulation. However, when we change the modulation phase, so in the beginning is sine. For example, later we change to cosine or minus sine and so on. What we do is that we are changing the phase of the time dependence in this big omega.
Okay. So would that
From the
suggest
details that we are still looking into? Yes.
would that suggest, like from your earlier discussion, then that you would want to change the sign of like the interaction between the lab and the
Yes.
and the system? Okay.
Right. Okay. Yeah, that's the basic idea behind this. Okay, but how to really implement this in the cleanest way is still, well, we're still kind of trying to study this. Okay.
Feng Shin, go ahead and ask your question. Feel free to unmute yourself.
Yeah, I have a question. You mentioned that when the particle in the boson firework jet, they're entangled with each other, right? But when you do the time reversal, what happened to the entanglement entropy?
What happened, you also, how do I call this, disentangle? So in the beginning, think about, so where's the entanglement coming from? In the beginning, all the particles in the ground state. Okay. And then you try to excite them. When you excite them, it turns out they are created in pairs. Okay, they're going in pairs. And then to some extent, you can say this is a result of momentum conservation. Particle going to the right, it should be accompanied with particle going to the left. Okay. And but now the reverse process is that the entangled pairs will interact with the BEC and go back to the BEC. Okay. So excitation will go back to ground state and excitation disappears.
And just a follow up, and then
Sure.
But in the experiment, we see the curves after a short while still goes up. So is that because it's coupled to the outside environment because of the decoherence stuff?
We believe, okay, so I guess it's possible. However, let me see. Let me go back to. Sorry. Let me go back to this. We were trying to see whether our irreversibility is coming from environment. What we check is the following. Okay, you can see we do have very good kind of understanding of if we do not change the phase, say alpha equal to 0, you set alpha equal to 0, and then this is the behavior of the system. We have very good understanding what happened to the system. We believe there shouldn't be too much kind of environmental noise or imperfections in the system. Okay, but saying that, I had to say we don't have a very good understanding here. We need to put in this is just an empirical fit. Okay, so we believe that environmental noise shouldn't play important role. Okay, but okay, this is just something that we don't have I'm not 100% confident.
Thank you very much.
All right. Let me see, what do I do? Okay. Okay, good.
Are there any other questions? Okay, well, Thank you very much for your time, Professor Chin, and let's give him one more round of applause. Thank you.
Thank you.